All right, well, I think we'll go ahead and get started. Well, first of all, thank you for joining us for another productivity webcast presented by Digital Dimensions. My name is Enrique Garcia, and this morning we're going to be talking about SOLIDWORKS simulation. This is a continuation on a previous webcast called Simulation 101, where in that webcast we were talking about basic part analysis, static analysis, and we were setting up pre-processing of the model and running the study. In this webcast, we're going to concentrate on the interrogation of your results, how you can go in and get some quantitative information, some qualitative information, and we will also touch on some thermal analysis as well. So let's talk about, this is going to be an overview of, or the breakdown of what our webcast will entail. First of all, we're going to talk about just the breakdown of some of the simulation products as far as tiers. There are many different levels of capabilities you can purchase when you get SOLIDWORKS simulation. We will talk about that and answer any questions you may have regarding that. Next, we're going to go in and review our assumptions with simulation. Just because this is a tool, it's not a do my job type of button or anything like that. So what we need to do is understand the parameters of how we're going to be testing our model so that we get adequate results. The results make sense for how we're going to be analyzing our models. So that's a very important aspect of simulation. Next, we're going to be talking about the interrogation of the model. Again, the qualitative results, quantitative results, and how to access that information. And lastly, we're going to be doing a thermal analysis. We're going to be doing a steady state analysis and a transient analysis on our model. So here's the breakdown for what we have as far as simulation products. If you have the highest tier of SOLIDWORKS, that's SOLIDWORKS Premium, you're going to gain access to the Simulation Designer package, which involves just the static analysis, so that just this particular box here you see there, that will be what you will be able to use. And that involves the steady state analysis of static analysis at steady state of parts and assemblies. You do have access to all of your bolts, pins, any virtual fasteners that you can model. We can put in virtualize in our models to simplify or idealize the model. The next tier is going to be the SOLIDWORKS Simulation Professional package, and that's the second tier, which involves all of the different types of studies you see in that particular box. One of which we're going to be talking about this morning, thermal analysis. The third and highest tier of the simulation package is the premium package. Now this is in a separate tier all of its own because we have the ability of doing nonlinear models, which are important. That's everything that involves plastic deformation. We'll be talking a little bit more about the limitations and assumptions. A side package we have from the simulation products is the flow simulation package. Now this is a CFD analysis software that we have with SOLIDWORKS. It's a separate add-in, a separate product altogether with its own interface, and this involves running and doing analysis on fluid mediums, both Newtonian and non-Newtonian fluids. So those are just the different breakdowns of our packages that we have for our simulation products. Is there any questions regarding this? All right, let's go ahead and continue on here. So let's talk about assumptions that we have to make when using simulation. So like I mentioned before, we have a separate product for nonlinear models that we can run. So what we're going to be working with today are just strictly linear or elastic deformation. Now when you think about a stress-strain curve, just picture in your mind a paperclip, and you're going to be bending this paperclip. The area or the section where we're going to live in for our studies is going to be this elastic deformation section of the stress-strain curve. So what this means, if I take this paper clip and I bend it a little bit and then I let go, it'll go back to its regular original shape. So that deformation we experience, that is our elastic deformation, that is what we can simulate with these two packages, the designer package, the static analysis, and the other professional package. Now take that paper clip and go in and add some more force to it so that it plastically deforms as well as elastically deforms. So it's going to bend, it's going to go back to some sort of similar configuration. It's going to have a little bit of elastic deformation, but it's definitely going to deform a great deal. That's the area that we can go in and use our nonlinear package and perform analysis on. That is not what we're going to assume for today's lesson. The next assumption we're going to make is that our deformations are small. Now we have to make this particular denotation or this assumption because of the equations we're running. We're using a set of equations, and the assumption is that all of our deformations are small. Now that's pretty subjective, right? Depends on your application, the scaling of what your models are going to be at when you're going to run the analysis or modeling your designs. So luckily the solver has a checker that will go in and will decide whether your deformations are going to be small. Now if the deformation is not small, then the software will give you a large displacement feedback. Now we do have a mode called a large displacement mode, which I will point out, and I believe we did point out in the previous webcast, but I do want to point this out once again. This large displacement mode is pretty much a fudge factor that will give you a ballpark answer to a nonlinear setup. So for our particular assumptions, we're going to assume that all of our deformations are small. If they're not small, the software will give us feedback so we can go in and run in this large displacement mode, and then after that, then do a true nonlinear study. The last assumption I want to point out is that all our loads are going to be static for the static analysis package. Now when we go in and we do a thermal analysis, we do have the ability to go in and apply loads in a time-dependent study, a transient analysis, so I will point that out and show that. But as far as our simulation designer study, like we did in the previous webinar and what we're going to be looking at for our results this morning, these loads are completely static. Our models and our studies are going to be at steady state. So let's begin, and we're going to interrogate our results from the previous study. So let's go back and do a quick review to show what we have done, and so we can all be on the same page. So last webinar we did a case study on this diffuser for the SB600 flash unit for Nikon's DSLR cameras. Now what this is for, it's for just photographers that want to have very nice diffuse light on their subjects. If you point this flash directly at their faces, you're going to have a very, very rough, very overexposed pictures potentially. You can see a lot of different wrinkles. Just the models don't want that. So you want to go ahead and have a nice diffuse light that shines on their faces to give them a nice effect. So this is what this does. And we basically modeled the design. We tested it in simulation with our last webinar, and we ran it with different solvers. And for this webcast, we're going to go in and interrogate the results. So we have a slew of different types of ways of looking at our results. So we break this down into three categories. First of all is producing the different type of result plots. You see that we have factor of safety plots, stress, strain, displacement plots, design insight plots, check plots. You can also save your deformed shapes. Now using these result plots, we have the qualitative results that we can gain access to. If you see at the bottom there, we have nice feedbacks with colors and exaggerations of deformations. This is all qualitative information that we can go in and pull from our models and from our studies. So we will talk about these different aspects of our qualitative result plots. In addition to that, without any body, we need a quantitative information. We need to be able to see certain points of interest. We need to figure out what the displacements were in certain areas that are vital to our design. We can grab that with the probe functionality. We'll be showing that as well. We can also take trend graphs. We can probe different areas in our models, and we can see qualitative information from these probed areas. Also, if you're using assemblies, I mentioned earlier, we can go in and virtualize and idealize our model. We can take an assembly with different bolts. Maybe you have a bolt pattern in there, and you can remove those fasteners from your study, and you can replace those with some virtual fasteners that we can model in simulation, and you can get information from those virtual bolts and see if your model, if your fasteners will pass or will fail a particular loading instance. So let's take a look at SOLIDWORKS here, and let's see what let's start to interrogate our model here. So this is our model, our flash diffuser model. Now let's jump into our static analysis that we are continuing on with from last time. So to give you an idea of what we were, the scenario we were simulating was that this flash diffuser was on top of this flash, and someone knocked it over with their hand or their elbow. Maybe this photographer was shooting at some event, and just some bystanders smacked it and deformed the diffuser. So we were doing that. We were simulating this by applying a fixed geometry condition onto the base of the diffuser. And we were simulating the load at a particular angle, and it's just a simple 1 pound force load on that face that we have here. We ran the study, and we have some results. So if you go in and you set up your options, we did this last webinar. We went into the simulation options, default options. And here under default options, we can look at each individual type of study, and we can tell it to pre-make a result plot for each study run. So we went in and we designated a stress, a displacement, and a strain plot to be created each time we run a new study. And so that is what you see here under our result folder. We have 3 different result plots. And I can go in and double-click to show each plot. Now, when it comes to our result plots, presenting our information is very, very vital as an engineer. You want to communicate your results effectively with all of your colleagues. So it's important to understand and be able to wield my legend here on the side. So anyone can go in and make a result plot and show it, but you have to make sure that your qualitative information makes sense. So what you can do here is you can look at your chart settings, and you can designate the color for this particular model. Now, why this is important, why we need to change up the color, that's because this particular, the solver likes to go in and likes to set the full range of your result plot in this in your graphics area. So what that could mean is that you could have some red areas that don't actually fail. So that's going to be a very important thing to go in and filter out. So to be able to change up your result plot so you can show adequate information, let me show you how to set up the chart options. So a quick way of doing this is to go into your legend, double-click, show your chart options, and you can switch this from automatic to defined, and this will go in and will allow you to present your results. If you have some red in there, you can make sure that you show that red is not harmful, so you can lower or increase the domain for this and be able to show your colors adequately. Sometimes, like in certain charts, we have a reversal of your colors. So if you have red, that actually means that it's good, but intuitively speaking, that's a bad color for most people. So you want to be able to go into your chart options, your color options, and go in and flip the color chart. So now to someone who doesn't look at your results, doesn't look at the actual figures, they might think this is a bad design. It's failing in most places. So again, representing your qualitative information it's a huge thing, huge responsibility. Any questions on the color chart options? Okay, another thing as far as result plots that I want to show is changing the definition of the result the result plot. To do this, you can either double click on an active result plot, and this will show you the ability to go in and change the type of plot that you've assigned to it. In this case, we have von Mises stress. Maybe I want to change that to my first principle stress. I can change that and click OK. This will change my configuration and my results. Or I can also right-click on the active config, select Edit Definition. I can change it back. Other important aspects to this property manager is the ability to change up your units. You can change your units there. Maybe I want to look at this in PSI. Change up my units. Also, I have the ability to change my results and to give you a more discrete look for your result plots. We can do this by changing our value type. So when you're looking at my results plot now, you can see that we have nice fluid color transitions between the different elements in my study. If I change this to element values, this will average all of the calculation points in one of my tetrahedrons in my model, and will give you a color assignment for the whole tetrahedral volume, and that's what you see here at the bottom. So it's a little more discrete. You can see a very clear denotation between the different magnitudes of my stresses here. Again, that's located under the Edit Definition menu under the Advanced Options. So node values versus element values. Also, another important aspect that I like to point out is my deformation scale. If you look here now, my deformation scale for this particular model is about 4 times the actual deformation. Now, SOLIDWORKS does this to make sure to convey the qualitative information clearly. So if I go in and I can edit the definition of the plot, I can go to deformation shape, I can change it to true scale, and then I can see what that actual true scale would look like. If I go in and manipulate my model, I can still see some deformation, but it's not as clear as it was before. So that's a powerful tool to make sure you check on or check off depending on what you want to see. Okay, any questions before I continue? Okay, next, it's important to be able to generate your own result plots. So instead of using the regular simulation options to automatically generate the plots you want, let me show you how to manually apply another stress plot or deformation plot. Do a right-click on the results folder and select Define Stress Plot, or Define Displacement Plot, Define Strain Plot. Simple as that. You select, you have all of your original options, so I can select OK. It's going to generate a brand new plot for me. Other types of plots that we have not touched on that we can generate are going to be your displacement plot and your strain plot. Again, same behavior. I won't elaborate too much on that. It's very similar to your stress plots, except for now you're showing displacement. Again, if you want to change your units, you simply double-click on the plot. You change up your units in your in this particular property manager. Same thing goes for strain. You can go in and change aspects of your strain plot as well. Another valuable plot that we can work with is going to be our design insight plot. Now, a design insight plot is great. This is something that was added relatively recently to simulation, and this is the ability to look at your models with the particular loading and fixtures that you have, so you can see how your strain carries through from your fixture to the applied area of your loading. So this will help models that need to reduce mass. You can see where your actually load requirements are and where your volume is set, that you need to not remove any particular material to keep that loading stable. Let me show you what I'm talking about. Go into the results folder, right click, select Define Design Insight Plot. And now all the areas that are denoted in blue are the areas that we can go in and that are vital. All these volumes are vital to our loading of our model. Now this will depend as far as the application will depend upon whether this is good information or not, because we do need the entire volume of this particular model for our photographer. We can't afford to remove any of this on any of these areas of mass. But if this particular model did not rely on this particular shape or geometry, I could potentially remove all of this area without affecting the performance of the model if it was hit at this particular area. Again, a good tool that will show you some different aspects of your model. Another type of result plot is the factor of safety plot. Now, factor of safety depends on your application, so this could vary greatly from the automotive industry to the bioengineering industry. We have different ranges of factors of safety. Now, factor of safety is a ratio that we have that involves the safety of our models. So if I have, depending on an application, my background is in biomechanics. If you have a class 3 device, you're going to have a very, very high factor of safety of 9, which means if this model needs to perform very robustly, let's say I have a paper clip that is a class 3 device, and it's going to be embedded into a patient's body. That particular device needs to operate 9 times the amount. Let's say I have a particular loading on this model. I need to be able to apply 9 times that amount of force on the model before it breaks, in order to have it have some insurance that it's going to operate successfully in the human body. So this factor of safety value is important for many applications. Let's go into the results folder. I'm going to right-click and select Define Factor of Safety Plot. Now I can go in here and I can choose what I want to test for a factor of safety. I'm going to choose Automatic. And hit the Next button. Now this is where I'm going to put my factor of safety. Multiplication factor, I'm going to leave it at 1. Now the actual factor of safety here is where I can choose what I want for my application. Seeming to have a graphics anomaly there. Let me close that up. Okay, so here's where I choose my factor of safety. I'm going to leave it at 1. So what this is saying is I have a force value there of 1 pound on this model. If my part fails, that means I have a factor of safety that's less than 1. So you definitely want to have a factor of safety of at least 1 or more to have a successful design. So in this case, if I have a factor of safety of 2 and my parts are not failing, that means I can withstand 2 times the amount of force applied onto this particular model before it fails. So that's another way of thinking about it. In this case, I'll leave it at 1, select OK. So I want to go in and show my maximum factor of safety, my minimum factor of safety. To show that, I need to go into my chart options. Again, a quick way of getting to there is by double-clicking on your legend. I'll go to my chart options. I want to show my minimum and maximum annotation for a factor of safety. And again, the coloring is a little counterintuitive to how you want to present your results. So again, red is not a good color to show a passing to show a passing aspect. So I want to flip my color assignment. Click OK. Let's take a look here. So my minimum factor of safety is 4.36. My maximum is 5 million, almost 6 million factors of safety units. So what this means, it's very robust here. And what it's saying here for minimum factor of safety is I can put 1 pound. So I can take this 1 pound force and multiply that by 4.36, and anything above that, that particular loading is going to fail for this particular model. So I think we're okay here. We have a really good factor of safety for this particular situation. So this is what you can get as far as result plots. Let's continue on and talk about interrogation, more qualitative interrogation of these result plots. Let's go in and show my displacement plot. And an aspect of your models that you want to go in and look for is not only the outside of or surfaces of your design, you could also have failure, or you could have displacements inside of your models, the inside volumes. So you can go in and interrogate your models by doing what's make sure everyone can hear me okay. All right, so let's continue on. So I can go in and continue to interrogate my models by doing a ISO clipping, or what's known as a section clipping as well. Let's talk about section clipping. If I do a right click on the activated plot, I can select section clipping. This will allow me to take any reference point. In this case, I can choose one of the planes, and I can take my model and I can step through the entire volume of my model, so I can look at what's going on inside of my volume of my part as well as the outside. Now you can do this many different times. I can have one section going up or down. I can select a second section. Maybe I want to do a right plane this time. So I can take a look at that model a little differently. So I can interrogate the model. Also, we have all of these different symbols that we have from our setup. I can go in and globally shut that off by going to my heads-up toolbar, going to my view settings, and I can shut off simulation symbols globally. This will clear up your models for analysis. So I can take a look at what's going on internally as well as on the surfaces of my design. Now to shut this back off, go back and right-click on that displacement plot, go back to the section clipping section, and then we have an on or off clipping option at the very bottom there. You can click that off, select OK or the green check mark, and now you can see the entire model. Any questions? Okay. Let me show what's known as ISO clipping. ISO clipping allows you to take similar degrees of magnitude and display them all at once, or it'll single them out, so it'll isolate them. Let me show you what I mean. If I go into the displacement plot, select ISO clipping, I can choose a displacement that I'm interested in. Maybe I want to choose 1 millimeter. So this will go in and show me all of the volume of my model that displaces 1 millimeter and up. So there's my cutoff, and I can see where this is located. And this works with all of your different result plots. This is ISO clipping. You can do a second ISO. I can show maybe the bottom as well. So I can show a very low degree of displacement as well, and I can see a nice domain between the two. So again, these interrogation tools are great for displaying purposes. I'm going to shut those off, turn it back on. Same little ISO clipping option. All right. So those are just some of the ways of going in and qualitatively interrogating your result plots. Now let's talk about going in and looking for some quantitative information. So we can do this by looking at my probe functionality. Let me go in and show the rest of my plot here. Let me go back into ISO clipping. Shut that functionality off. Now let's go in and see, maybe I want to know exactly how much deformation I have on a particular point on this cylindrical surface. To do that, right-click on the plot that's shown and select probe. After you select probe, I can choose at location, from a sensor, on a selected entity, or the actual distance. So if I'm interested in a particular area, I'm just going to click on that particular point. Now, from previous information, we know that SOLIDWORKS can't afford to sample every single area of volume in our model. So it goes in and samples, and wherever I click, it'll select the closest node possible that's in one of my tetrahedrons. So in this case, you see where my mouse is located. At the very point, there happens to be no node, so simulation chose the node that's right above that, that's closest to my area of selection. In this case, it's going to be that particular node, 4,926. I have my magnitude there, my displacement. I can also go in and pick additional nodes that are on the side maybe, something like this. And I can go in and I can take a look at them all together. I can also go in and look at the trend. I can plot these points so I can see that my displacement is actually going down as I'm leaving that red area. So I can see the trend this way. Let's take a look at some other plots as well. Let's look at our stress plot. Let's look at this one here so we have a better color assignment. Let's take a look at our stress now for this particular plot. Let's go in and we'll do a probe. Or I can also do probe, or I can do list selected. List selected will give you the same probe interface, except for it'll give you a different bullet here. It'll say on selected entities. So what this will do, this will allow you to choose any edges or surfaces or solid bodies, and for that matter, and it will go in and select all of the nodes associated to that entity. In this case, I'm going to select that particular edge. I'm going to select the update button. It's going to look at all of my nodes that lie upon that edge. Now I can select plot, and I can see what those values, those magnitudes are for each node. Now you can go in and you can save this information out. Just go to File, Save As, save it as a CSV file, JPEG, PNG. Now, if you're interested in a particular area that's an exact point or volume on your model, you can do one of two things to be able to sample that and force the software to sample that. One is you can create a split line, which we covered in our last webinar. That would be what you see here for this model. Let me hide my plot so you can see my split line a little better. So I created a split line, and I basically scored the outer surface of this cylindrical face so I can be able to select things of interest, in this case the surface, so I can apply a force on it. But what this is good for is if I go in and if I show my stress plot, I can probe a particular area, in this case those corners, those exact corners, and I know the software had to go in and sample those corners. So I can take and I can sample these particular precise areas of my model. Now, if you don't want to go in and do a split line, what you can do is you can add a sensor to your model. And adding a sensor is actually a SOLIDWORKS functionality. I can go back to the SOLIDWORKS model, the 3D CAD model. I can go into the sensors folder. That's up here by default. I'll right-click and select Add Sensor. I can go in and select Simulation Data. I can choose Stress. I want to have it record von Mises stress. I can choose the units, megapascals. I want to choose the maximum. Or I can choose several different Boolean operators and ranges. I can choose maybe maximum over selected entities. And then at this point I can go in and I can choose a point of interest. And this sensor, once you click OK, it'll assign the sensor. When you rerun the study, you can go back into your results plots, and you can go and probe that particular model. This from sensors will be shown. You click on it, that particular sensor will show up with that point assignment, so you can give yourself some assurance that it did sample that exact volume or 3D point in your model. Okay, that's how you would go in and you would probe your graphs. Now, I mentioned earlier that we can go in and grab some information from some virtual fasteners. These are just different connections that we can simulate with the software without having to actually bring in the model, these little pieces for our models. Now, the reason we do this is that we don't bring in all of our bolts and fasteners into simulation is we want to keep our models simple. Our studies have to be simple at first so we can make sure we have a sound study setup. Also, a second reason for keeping your model simple is because we have to go in and sample the entire volume with different points of calculation. Now, these points of calculation are known as are what's called a mesh. So if I go into this mesh folder, I can show my mesh and I can see what I have for my points of calculation. So each area where we have some convergence of these lines, each of these areas is a calculation point where the software has to go in and solve our equations and give us results. And aggregately, that's what we go in and sample, and that's how we grab our information. So as you can see, if I have a bolt or something, if I have just an array of different fasteners, I have to apply many different nodes of calculation onto these small, tiny surfaces or the volume, and this could eat up a lot of your RAM resources. So again, this is why we idealize our simulation studies as much as we can, and then at that point, once we have some good results, some initial results, you can go in and add more complexity to your study setup. So if you go in and you insert some of these bolts or pins or springs into your studies, you want to go in and see some information on these particular idealized fasteners. You can do that by right-clicking on the results folder and going into the list pin bolt bearing forces. In this case, I don't have anything that I've assigned to as far as any bolts or pins. In that case, if you did have anything, you would see that. You would be able to see some normal forces. You would be able to see if your models pass or fail. If they break and they yield, then you'll get some information on that as well. So that we will cover on any future webcast as far as analysis on assemblies and multi-solid bodies. All right, any questions so far on anything we've covered? All right, let's go ahead and switch gears. We're going to take this model, and we're done interrogating this model and getting some information from it. Now we're going to take and apply another type of study to it. We're going to do a thermal study on this flash diffuser. So the application that we're going to simulate is going to be the thermal loading of this particular geometry when you apply a flash from the flasher that it sits on. If I go back to my graphic, you can see how it sits on top of my flash. That's my camera body. This whole unit on the bottom is my flash. And let me tell you some specs on this particular flash. So each individual flash, or each cycle, outputs, I think it's a maximum of 3,000 watts per each power burst. So that's quite a bit. So we have to be able to have this model withstand at least a couple of bursts of flash every couple of seconds in order to have a good design. Now the speed of this flash is going to be important. Each flash executes at 1,000th, so 0.001 seconds per flash cycle. So that's extremely fast. So when it comes to the magnitude of temperature that's going to be affecting this unit, it won't be the whole 3,000 watts, and also it's not going to be as the magnitude won't be as high as what I'm trying to get at. Also, we're going to assume that my heat power is going to last about 1/10 of a second for each flash cycle. So we're going to be modeling one cycle, so one flash, and we're going to be modeling this for 2 seconds. So upon 2 seconds, we're going to flash it once, and we're going to see what our temperature distribution will look like on this model. So here's some assumptions we're making here. So there's some of the information we're saying about the power bursts for the flash. We are going to apply 2,000 watts as a result of conduction for our models. So when it comes to thermal analysis, what are we actually looking at for here? Our primary unknown for a thermal analysis is going to be temperature. Temperature is going to be important. We're going to see what's the highest temperature. We want to make sure we don't melt the material we're using. In this case, the material for this flash is going to be a low density polyethylene plastic material. And looking up the information for that, it's going to be about 221 degrees to 239 degrees Fahrenheit for our melting point. So that's going to be a marker we're going to make sure that we don't pass. As far as other mechanisms that we use for heat transfer, we do model conduction, and that's done just by touching solids or solid types of solid bodies together, and we can go in and we can add thermal resistances. We can simulate that as well. Other types of heat transfer mechanisms is convection. So when we apply a heat power to this thing, we're going to apply 2,000 watts onto a certain area of our geometry. We're going to go in and tell this thing how we're going to be having heat escapage through convection. We can do free convection, which is what we're going to be doing today. We can also do forced convection, which we're going to also talk about. Forced convection, we're going to go in and specify certain surfaces of interest, and we're going to give it a convection coefficient, so we can tell it exactly how much heat is escaping the environment or this material, so we don't have just an aggregation of all of our heat power. Lastly, we can also simulate radiation. So radiation is the only type of heat transfer that we don't have to have a fluid medium with. It can be a solid, liquid, or gas going through a vacuum. So let's take a look at thermal analysis. So the first type of analysis that I'm going to do for thermal is going to be a steady state thermal analysis. So let's set one of these up. Any questions before we continue? All right. Well, let's create a thermal analysis. Now, if you have a simulation professional, you're going to see a whole slew of different types of studies. If I start a new study, I'm going to see it maybe up until the fatigue analysis. If you have simulation premium, you're going to see the last three here, or excuse me, the last two. You're going to see nonlinear and the linear dynamic. Let's go in and let's create a thermal analysis. We'll go ahead and call this steady state. Okay, you can see that our material assignment was brought in from our previous studies and our material assignment from the CAD model. Connections, I don't have any connections. And connections, I did touch on this on our previous webinar. This is a way of applying, if you're familiar with SOLIDWORKS, this is basically adding your restraints to your different solid bodies. So you can add, in this case, the thermal resistance through different surfaces, but you can also apply your regular contacts, such as bonded, and I can insulate certain surfaces here. So we will have another webinar regarding assemblies. So that's connections. I don't have any connections that I want to apply. This is one part. I do want some thermal loads, so let's right click, and I want to apply a heat power load on my model. Now again, I'm assuming the whole 3,000 watts are not going to be applied to the model directly. Most of it's going to be shot out just through the top there, and it's going to bounce off of the ceiling or something of that nature. But we are going to have some models that are going to be, or some aspect of our design that's going to be affected by heat conduction. So we are going to assume, just for the sake of our presentation, that this whole surface will be affected by this heat conduction. And we are applying a heat power to all of this surface. We're going to apply a 2,000 degree or a 2,000 watt heat power to that. Select OK. Now we're applying heat to our system. Now we want to make sure that we can have heat dissipate or leave the system. If we don't do this, we're not going to get accurate results. You're going to see that our models are simply going to be red. You're going to see like 22 million degrees Fahrenheit for our temperature. It will be a false reading. So you want to always make sure that you have some way of having your models have heat power escapage. For this, I want to do a right click on thermal loads. We're going to do this through convection. Now, convection, for this particular coefficient for convection that we're going to choose is going to be 20 units. So I'm going to type in 20. And now we have to give it some sort of reference, just because this is the way the equation works is a change in temperature. we want to make sure that we can have the software figure out what the temperature will be at the surface and what the ambient temperature is going to be, which is going to be room temperature. So let's put in 300 degrees Kelvin for that. Now the areas that are the surface area that we're going to be designating as our convection is going to be as follows. And again, this will definitely take into account or actually be significant for our results. So everything that we do here, every assumption, every type of fixture that we apply is going to be important for our results. If you have incorrect assumptions, you have incorrect setup, you're going to have incorrect results. It's just the garbage in, garbage out principle. If you have good information coming inward, you're going to have good information coming outward, or logical information. I'm just going to select I'm not going to select everything, but just a good slew of different surfaces for heat escapage. That's good enough for our study there. Good surface area coverage. Once we're done, I'm going to go in and run the study. Just a quick review for the different solvers that we have available. To gain access to the solvers, you want to go into the study properties, do a right click on the top level of your study, go to properties, go down to your solver. A general rule of thumb that if you don't know what type of solver to use, don't worry about it. Let the software figure it out. Choose automatic. If you have more of a smaller type of model with less degrees of freedom, then you want to go in and pick direct sparse. That's going to be it's going to solve your models just a little more efficiently, a little quicker. If your models are huge or you have a lot of RAM at your disposal, you definitely want to go in and use the FFE plus solver, and this in the long run will solve a lot quicker. But again, if you're not sure, then don't even worry about it and just choose the automatic solver. Let's go in and run the study. Forming our mesh. We'll let it run there. There's our model at steady state. Now again, we have one default result plot, the thermal plot. I want to add another plot here. I want to add a heat flux, a resultant heat flux. I want to see which areas do I have the most heat power, or Q dot, passing through my volume. So to get this particular rate information, I want to do a new plot. Right-click on the results folder, select Define Thermal Plot. I'm going to go in and change my result plot. I'm going to choose, I have a slew of different types of result plots here. I can go in and segregate per different direction as well. I'm going to choose resultant heat flux. Select OK. Pretty non-significant here. Let me take a look here at that. Let me change my units there. I'm going to choose floating. That's my heat flux. Let's go in and let's sample the thermal study. Now let me change my units from Kelvin to something more understandable for me. I'm going to go in and change that. I think I'm going to leave my plot domain alone. Let's go in and change up my units to Fahrenheit. Now I mentioned that melting point for this particular material is going to be about 240 degrees Fahrenheit. Let's take a look at what we have. It's quite high. It's definitely way higher than 240 degrees. So in this case, we know that if we apply a 2,000 watt heat power to this model, it's going to definitely melt, right? But there's no way of getting around that. So luckily, that is not the application of our design. We're going to go in and apply small bursts at 2,000 watts. And we're going to apply this at 1/10 of a second. So it's going to be important. So let me show you how to go in and take this study, and we're going to make a transient analysis or a time-dependent analysis. Any questions before we continue? All right. So I've went ahead and I pre-made a transient thermal analysis just because it does take a lot longer to actually solve this study. It has to go into every single time step and solve to get some accurate results. So I went ahead and did this beforehand, and I want to walk through the setup. So let's take our model here. So the first thing you want to do is, just as before, you want to go into your new study, create a new study, select thermal analysis. After you do that, you'll have this particular setup. The first thing you want to do is designate this as a transient analysis. You do that inside of your study properties. So you right-click on the name of the study, you select properties, and at the very top here, you have, under your options tab, you have the ability to switch from steady state, which is by default. You want to switch that over to transient analysis. Now below that, you get an opportunity to select your time domain, or your overall study length, and the time step for your model. Again, the finer the time step, the more resolution you get for your results, but then again, the longer it will take to run. In this case, I'm going to do a 0.02 step of a second for a total of 2 seconds. Again, my setup for this, my area that I'm going to be modeling or simulating this is going to be going in and applying one cycle of flash to this model to see what's going to happen to my temperature. Also, some other aspects of this, I can go in and grab information from additional studies. If I wanted to, I could go and I can select the initial temperature from that steady state analysis, and I can port that into this additional temperature. This is if I want to grab the loading from that previous analysis. So that's not what I want to do in this case. Let's go ahead and leave it to transient, 2 seconds, and my certain time step. Select OK. Also, thermal loading, I want to apply a new type of condition on this. Because we are working with a time dependency, I need to have some initial conditions for my environment. In this case, I want to tell the software what my overall volume is at time 0, time t, for this whole volume of my model. I do that by right-clicking on thermal loads, selecting temperature. Now for the temperature box, I have 2 radio buttons. I want to make sure I choose initial temperature. This will be my initial condition. And I want to choose my entire volume of my model. Now for new users, what they usually do is they select all exposed faces, and it looks like I've selected the entire model. This is very, very wrong. What you've actually done is if you've chosen all of the outer and inner surfaces there of the model, but not the internal volume. So you want to clear that out, and you want to go in and choose the whole volume of the model. To do that, I can go into my design tree, expand my design tree, go to my solid bodies folder, expand that, and choose the actual solid body from the tree. This will ensure that you also assign this particular temperature to all of the internal nodes of the volume. And here's where you can go and specify your temperature, which is going to be 300 degrees Kelvin. You'll click OK. And I've gone ahead and done that already here previously. One important thing I want to point out as far as this solid bodies folder, this is pretty handy when you're an FEA analyst. You want to make sure that you have access to all of your solid bodies, even if it's only one solid body. Now, if you have more than one solid body, this solid bodies folder gets shown automatically. But in this case, if you have one solid body, the SOLIDWORKS software assumes that you don't need to just be able to click on the solid body. But as you can see, that's not the case for us. So as FEA people, we want to make sure that we show the solid bodies folder at all times. Let me show you how to turn that on in your options. This is going to be under your SOLIDWORKS options, under Systems Options. You're going to go under your go under your Feature Manager. and then under solid bodies, hit the flyout and change it from automatic to show. And this will ensure that the solid bodies folder will be shown at all times. And again, this is a system-wide option, so this only has to be done once. Again, very valuable little tip. This way, you're not left to going in and trying to figure out how to grab the whole volume if you have one solid body. Any questions so far? All right. So again, we've done a transient analysis. We've designated the time domain and the time step. We gave it its initial condition of room temperature for the whole volume. Now we can go in and run the study again. Now I ran the study. As far as our mesh, I chose the regular mesh. Let me show you what that mesh looks like. Now a quick review on mesh. There are two ways of applying the mesh. You can do the standard mesh, and you can do what's called a curvature-based mesh. Let me show you what that looks like. I'm going to go in and right-click on the mesh folder, select Create Mesh. I'll say OK. Now, the software looks at our geometry and gives us a good averaging of what the element size should be for the particular model. In this case, it shows 0.16 inch for the overall size for each element. So you can take the slider bar and roll that higher for a more fine mesh. This will give you more points of calculation and will also increase your accuracy. Now, you don't want to get carried away with increasing the accuracy on this, just because the higher you get, the more points of calculation, the more time it'll take to run the study, and potentially if you have a lower end system, you could crash out your system and it might become unresponsive. You might have to go in and redo your stuff. So be very careful with this. Know your limits of your hardware before you begin to bump up this value. If you're in the process of exploring the limits of your hardware, do a save as or do a pack and go of your assembly, or a save as copy of your part file. Run a study multiple times. Close all your other softwares down. Only have SOLIDWORKS, and increase this value until you can see what your limits are to your hardware. It's a very important step before running a full-blown FEA analysis. As far as going in and sampling your study, we have two modes, like I mentioned before. The standard mesh, we'll take your model and we'll just pepper your model uniformly with all of your different points of calculation. Now, also we have the ability to do a curvature-based mesh. The curvature-based mesh is more what you see here, and I lost my my previous mesh. But what that does is this takes areas that have different inflection points, different curvatures that are greatly changed, like you see here at the bottom, these fillets, and that will automatically add more points of calculation on those areas and less on areas where the curvature does not change as much. So those are your two flavors of models. If you're going to be doing something more organically shaped like you see here, then definitely use curvature-based mesh. If you're doing very prismatic, blocky parts, then stick to standard mesh. Under Advanced, we have what's known as Draft Quality Mesh. Now, if this is your very first study, I always recommend turning on Draft Quality Mesh. I definitely, if you're not familiar with meshing your models, please look at our previous simulation webcast. It was called Simulation 101, and that will cover this in great detail. But just a quick review is taking Draft Quality Mesh, turning this on will make sure that we only have a more limited amount of calculation points. You want to do this for your initial study because you want to make sure that your study setup is sound. You don't want to have any extra points of calculation to slow down your study time and your calculation time. Your initial study should be to make sure that your setup is proper so that you can have a baseline for your results and then work up to your accuracy, work up to an accurate result. So always have Draft Quality Mesh on for your initial studies. Let me back out of here. Or any last questions? Any questions on the mesh? Looks like I do have some questions here. Let me take a look. There we we go. I have a message here. It says, when the program is running a simulation, does it use only RAM memory, or can you have it set up to write to the hard disk while running the study? Very good question. We are a RAM resident software, so it will use physical RAM first. You can go in and work with your virtual memory. Just go onto your systems, your control panel. If you're on Windows 7, you can type in paging file size, and you can gain access to the virtual RAM on that. But what happens is it pings your video card's memory first. Once it runs out of that, it will go in and access your motherboard's RAM memory on that. And if it needs to, if it runs out of resources at that point, that's when it'll go in and pull from your hard disk for extra RAM. Now, I don't recommend it getting to that point. If you do run on like a standard hard drive, your revs on that is 7200 or at best, right, or 5500 if you have a low-end hard disk. That's very, very slow. So if you do run into the situation when you run out of RAM, and you might get a feedback that'll say out of core. It's a message that'll say out of core, and that means that you've reached the peak of your RAM resources, and now that you're hitting the hard disk space. If you reach that, you're very critical. I recommend not touching the computer whatsoever. If you're interested in salvaging your result, let it run through that particular study at that point. If it does need more RAM resources and it runs out, it might crash if you don't have enough hard disk space as an auxiliary for your RAM. So definitely set that up adequately. The faster revving hard disk that you have on your machines, the faster it'll run. But you will see a significant decrease in speed when you're solving your calculations when you're running on your video card and motherboard regular RAM to when you're running off of your hard disk for extra resources. You will see a huge drop in speed, and it'll take a lot longer to solve your studies. So be mindful of that. If you have a steady state drive, you're at a really good advantage. You're going to see not so much of a decrease. You will still see a significant decrease, but it'll be a lot better than those of us who are revving at 5,500 RPM. So, any other questions regarding that? All right, let's go ahead and take a look at our results here for this particular plot, for this study. So we ran the study. It took a couple of minutes to run this. At point 1, it was 0.02 seconds was our time step. So let's take a look at our results. So what we have here is our results, and I can tell you what our time plot is. Well, let's take a look at our temperature there. We can see that our maximum temperature is 185 degrees Fahrenheit. So at one pulse of this particular model, we're telling this thing that we're not melting. Our model is not melting, so that's good news. Before we look at the rest of our plots, I want to point out one important thing I forgot to mention as far as how we simulated our scenario. I mentioned that we're simulating one pulse of our flash, and to apply that, we changed our heat power. If you look here at our heat power, let me go in there and talk about what I've changed. I'm going to go in and edit the definition of the heat power. Again, we chose the same inner surface for that. What we did change, what we also added was a time curve. Now, a time curve allows you to take your whole time domain. Let me edit the curve to show you what that looks like. And this time curve allows you to put in a magnitude for this model as a function of time. So my first column is going to be seconds. Again, our end time there reminds us is 2 seconds. And at this point, at 0.06 seconds, I said I want this magnitude to be 100%. So what the 1 stands for is a whole 2,000 watts. So from 0 to 0.06 of a second, I have this magnitude increasing until it peaks at 2,000 watts at this particular point. After that, I told this thing to stay pulsed for a total of 0.1 seconds. At that point, I wanted the magnitude to be all the way back down to 0. So effectively what we're doing is we're giving it a time dependency, and we're telling this thing to spike up. If I can view my plot, we're basically taking it and we're increasing the magnitude of the flash. We're representing the heat power due to the conduction of that flash to the plastic, and it's peaking there at that particular time. It's going back down to a magnitude of 0 at 0.16 of a second. So that's the amount of time that this particular temperature is acting on the model. The rest of my temperature, as far as when I look at my heat gradients, my temperature gradients, will be a response to this particular heat power. Also, other things that you can do as far as inputting for your temperature for a transient analysis is a thermostat. This is a great little tool. I can go in and choose a sensor or an area. This works just like your air conditioning units at home. You can select a sensor, an area. After that, I can choose a cutoff, a lower cutoff, and a higher cutoff. And what this will do, this will apply my heat power at 2,000 watts. And once it reaches a higher cutoff, I can tell it to shut off, and then my temperature will start to decrease and decrease until it reaches a lower end. Once it reaches the low end, it will turn on my heat power again, essentially giving you a sawtooth effect for your temperature. So you can see the effect, the aggregate effect of these of the heat power being turned on and turned off over a certain length of time. Very, very neat tool there. Any questions on the thermostat tool? All right, well, let's close this out. Let's take a look at our results here for this particular flash. Like I mentioned before, after this particular flash, assuming that my setup was accurate, all of my assumptions with applying my 3,000 watt power, only having 2,000 watts affect the material, and applying this particular loading, this is my result. So if those assumptions are correct as an engineer, then my model should perform. I should not have a massive failure to this part thermally. In this case, 185 degrees Fahrenheit is significantly less than the 239 or 240 degrees Fahrenheit for my melting point. So I'm doing good there. This is for one cycle of flash. So there's my denotation for maximum there. Also, some other things that you can do as far as some qualitative information is you can animate your results. If I right-click on the result, I can go in and select Animate. I'm going to go in and I can do 2 seconds. I can show what that looks like, and I can have it sample through. It's currently doing its calculation to show this time with my time domain between 0 and 2 seconds. It's got a lot of data to process, and there it is. It's 2 seconds. Again, you can increase or decrease the frame rate by taking the speed slider, moving it left or right. So here pretty soon you're going to be able to see a pulse here. It's running through. Look at my time domain there. There's my pulse, and then there's my time reaction, or my temperature reactions from that. Now, this is also available in all of my other studies, from frequency to drop testing to static analysis, and you can save all of these as animations, as AVI files. Let me pause this or stop it. I can go in and select Save as AVI. I can go in and I can choose a compression factor if I want to get techie on that. And let me just choose, I'll just save it to my desktop. I'm going to hit play, and once you play, this will go in and start to write to my desktop. Let it calculate, and now it's playing the animation. Notice how it's saying creating frame where my mouse is located. Once it's done creating frame, I can stop the animation, and then I can look at my results. I can look at this AVI file we've created. Almost done. There you go. creating my AVI, and then we'll go ahead and take a look at what that looks like. Again, you can compress this or leave it full frame depending on your application to affect your actual file size. Looks like it's still cooking here. There you go, creation of frames completed, playing animation. I can stop this. Now I can go in and browse to my desktop. And it's this SB600 diffuser. I can double click and show that in my default browser, and there it is. Again, just that pulse there. And you have the ability to go in and tell it at what frame to stop and start it. Close that with my different options there. Any questions on animations? All right. All right, I think that's all I have for us to show. Let me see, I'll go ahead and leave this open for another minute or so, just to ask if you guys have any questions there. To give you some closing statements here, if you're wanting to go in and look at webcasts or more training information, we do have a simulation training available at all of our different satellite offices, so go ahead and call in for that. We do have some Tech Center tech tips. If you visit our website there at ddicad.com, feel free to browse around, go into the support flyout. You have access to all of our different resources available for you. We also have a podcast that's done and presented by Lou Gallo, and it's called SOLIDWORKS Heard, and he does a weekly podcast full of good technical information as far as what's new as well, and good CAD news related to SOLIDWORKS and simulation and all of our other products involving Dassault systems. Go ahead and stay tuned for some more productivity webcasts, and thank you for joining us this morning.